Now, we are continuing with the afternoon session with the Keynote series. I will leave the microphone to our Keynote speaker, CTO of Huawei Wireless, dear Dr. Tong.
Okay, thanks for the invitation. I would take this opportunity to share some of the status of, in terms of 6G research and the standardization. For the past, let's say, almost 8 years or 6 years, academia and the industry started with exploration of 6G. So the news of today is last year, International Telecom Union, ITOR, already defined what is a 6G. Now, industry from this year, actually next year, to step into the standardization. By the year 2000, we will have standards. But what 6G will really looks like, or what we want 6G to be, or where is the direction of a standardization should go, that's the topic I want to share today. So first of all is a very quick snapshot of what we think is this direction. The second is why the 6G right now is experiencing a true revolution. So the 5G is a success. In the market realization, almost 30% or 40% population already on 5G network, and then the slow progress of the 5G is the to be as a nature of a vertical business. So this is the timetable for 6G. There are 5 major milestones. Number 1 is in the actually October this year, there will be a S1 study on the use case of a 6G. And then next year, first quarter, we will have a industry very important 6G workshop in the 3GPP standards. And then in the next year, this time, there will be a study item. That means the industry will study what is a 6G in terms of standards. And then in 2026 or 2027, in the early that time, there will be formal standardization. It's a number 4 here process. And about 2030, we will have published standards, and then industry will go commercialization. So you have a feeling that there are 6 to 8 years to shape what is 6G will be. Then there will be many views on what will be the 6G. So in our opinion, 6G will be a true generational technology disruption. So what I meant is look at the right-hand chart of this. Every generation we have a magnitude of all the improvement in terms of spectrum efficiency and the per bit of the energy. So because the technology of 6G will be used for 2030 and 2040. At that time, today we are very difficult to imagine what is the application or service at that time. So from the very beginning, or day 1 6G, 3GPP standards need to adopt a disruptive technology to enable the capability of improvement to sustain that horizon over time. And then 6G should be not another way of implement 5G. Instead, 6G should generate the market value for next decade. One important thing is for the past 20 months, there is a truly going on the AI revolution. So if we miss this opportunity of this AI revolution, then our industry will become irrelevant or obsolete. So 6G should embrace AI revolution and with this, together with this so-called quantum leap jumping. On that side, AI is in the months of every 2 months of one revolution, every 1 year have a 2 model that speed. So on the core network side, we need to use AI to completely generate automation of the network. On the RAN side, we need to enable the embodiment AI or AGI as an object rather than a smartphone. Then the UE side will be fully intelligent. So in that case, the many new form of terminal will be emerge on that time. And then 6G architecture should be an innovation rather than stay in the 5G architecture we have today. This is because the current requirement or the service that operator have it's sufficient to be fulfilled by 5G advanced. So 5G advanced cover the current requirement, and the 5.5G or 5G advanced is the right technology of a choice. But then simple reuse 5G network will, without the foundation change or improvement, will hinder the AI revolution in the next 10 years because that is a different world. The last is the question of smartphone. Smartphone is already 70 years. So it's very hard for us to imagine that 2030 we will still stay on the smartphone. So the AI or the device breakthrough is really needed in order to take us into the new generation. So in a nutshell, in our view, to this forum, is the message is 6G technology is an innovation technology, not a 5G extension. 5G deployment is doing well, and all the current requirement and service can be fulfilled by 5G advanced. And this will protect the investment of the industry or operator that put into 5G already. And then all the 6G just simple copy, which is in my view, is not real 6G. So we should not underestimate the capability of 5G advanced, and we should definitely will be mistaken if we underestimate the power of a 2030 to 40 that technology revolution, especially in AI. Then what I meant to that, look at this picture. So 2022, since the birth of ChatGPT to today, the large language model is mature to a certain level. Now from this year to 2026, we don't talk about large language model anymore. It is called AI agent. The last week or 2 weeks ago, the OpenAI released the 1.0. That is basically the announcement of the finish of the over of the ChatGPT. They don't call GTP anymore. So this is a new model that can be to a certain degree or most of the degree that they solve the problem of the expandability, reliability, and it is still a black box, but it's the other technology. So 2026 to 2028, that Sam Altman yesterday was in his blog was saying in 1,000 days we will have AGI. That means the artificial general intelligence. And then 2028, 20 to 30, that's our job to connect these AGIs, not the smartphone. So that's where we need to enter what is actually the innovation take us. So number 1, 2, 3, 4, 5 button is the definition of the level of intelligence. Chat box is basic level. Reasoner, that is a 1.0, that is the already released in the market. So there will be agent and then innovators and then organizations. So the rest of my talk is built on the agent technology. So explosion of internet, the agent is on my right-hand side the circle that they have the four basic property. One is it can make reasoning, they can have a sensing, they can have a reasoning, they can make a decision, and they can take action. So this is not a model that you can do only question and answer or chatbot. They can do reasoning, decision, and answering. So the curve you show here, we show you here is the ChatGPT 4 level with that model in terms of the level of the token that efficient or computing efficient complexity. So you go from 2028 to 2030, we are entering super intelligent states. So the white dot is the point of the AI agent or agentic AI. What really happening is the Apple announcement of an AI phone. That is, the phone is not a OS, app, or some processor anymore. It is a phone will have only user interface, perhaps the only use natural language, and then you go direct to compute the large language model and then GPU. With this phone, you can as well do this agent property, as I mentioned before. And in the network side, can build an agent as an engine to automatically assemble network and run the network. So this is the structure of an agent. So you see large language model is one of the key components, but it's not the only component. The component we have is can do planning, reasoning, and then have tools, and have the memory, and then we have this simulation that has a sandbox to validate everything before we use this solution. So what do we mean 6G? In that case, 6G diagram is on the left-hand side. I think you in this forum and many people talk about this before. So that every element in the end of the day at the 6G will support AI service. So in that sense, the 6G become a AI agent as a platform for you to provide a service and application. So the agentic AI, as I mentioned, is a large language model can use tools. It's not a model that to answer your question, but it can model to take action. So in that case, we have a so-called agent-based bus or interface in the blue. This is the derive of the 6G network architecture. So we have a planning on the left-hand side capability. They can do reasoning. They can do Monte Carlo Markov chain decision. That is reasoning, and they can do chain of thoughts or dividing of sub-goals. And then tools. There are many tools like 3GPP as one tool, Internet Protocol is another tool. So all these are the ground truths of the tools and the rules that you need to build your network. And the memory is that basically the log of your operating, your history of your network operating. And with this, you can basically automatically generate a piece of software as a networking. And then you simulate this or validate this as a valid one, you can build your 6G network. This picture is what is the network architecture looks like. But we need something like a planning agent, a sample agent, and a connection agent, and an execution agent, and sandbox. In the bottom, you know, or you all know that there is a UE, there is a RAN, there is a network slice, and some computing resources, spectra. So this is the network. So in the production time, that means any operator will have this piece of a platform to produce the network slice. So you from plan agent, you go to a sample agent, and then you do connectivity agent, and then you go to a sample agent one more time, and then you execute what is your software running in the sandbox and come back to do this. After a couple of iterations, you have a completely piece of a slice of a network. And during the runtime, you can run this through the actor with the execution agent. You do reinforced learning to optimize the runtime and as well as the optimization of the connectivity, meaning the throughput, delay, and all the other stuff. So the basic, what you will get is the application. Once you have a natural language, you will specify what you want as an application. Then the software, the AI platform will automatically generate a network for you. So this is the plan agent, and so this agent will work together. So when it runs, in the extreme case, once the application trigger a network, once you finish the application, the network is not there anymore. With everything is so dynamic and automated. It's called a network application-driven network. That's the core part. Now I'm getting RAN part. So in the case of a communication, when AI become the service, the bit doesn't matter. The meaning that it is the intelligence or the effect or the effectiveness or sometimes a semantic is really important than the bit. So information is not equivalent to understanding. Now we need something to communicate in the network by understanding. So in the case base, the model is the AGI to talk to another AGI. So what is the machine for the AI for the large language model is now called a transformer. So there are two types of a transformer. One is an encoder and decoder, or some decoder only transformer. But for the communication purpose, we need this encoder and decoder transformer. The red line that's where it's the so-called intelligence transmitting through in the network is the token. Now the communication is not a bit that important, it's the token we need. And then transformer is a predictive generative AI in terms of generate token. In the transformer structure, when we map into network, they are part of it it's in the device and also in the edge and also in the cloud because of the computing capability and the power consumption. In the case, in the AI time, basically data may not be important. What we all need to transmit is the model. So there will be model over the air, model around the edge, and the model goes through the cloud service. So many types of model. In the ultimate network, there is no data, but it's a model communication. That's where we need to add in the standards in the RAN part called AI RAN with the sensing, local data, and the model setup with the communication, URLC, MMB, LLC. And then the RAN is not connectivity anymore. It is connectivity plus sensing plus AI. At that node, it becomes an intelligent node rather than just passing through the bit. One more thing is that because we are sending wireless signal and that wireless signal can sense the real world. And this real world model is very important for building the embodiment AI. That means the AI show up in the real world and they know how to get things done. So this is the unique value for 6G network to provide the world model. As an example, so there are several devices in the room, and then they can do the sensing, and with the sensing data to collect to the node, and they can do use AI to reconstruct the physical reality on the right-hand side. With that, we can do sensing-assisted communication and communication-assisted sensing. As well, we can use the real world to build for the AI service in the end. So the takeaway message is the application or the future service will be truly AI enabled. Then if we use a non-AI, non-intelligent network, will be the barrier for those services to be efficient. So therefore, 6G need to be intelligence itself, not by core network as well by some the RAN radio portion as well. Then to repeat, it is a truly opportunity all the time for generational technology disruption because the AI revolution. Second, it should embrace this revolution, otherwise we will be irrelevant. And the third, the architecture should be continue to evolve to support the intelligence, and the user device need a breakthrough. So in a nutshell, 6G is not for smartphone, it's for the AGI. Thank you.
Of the network to support. Did you hear me? Or?
Yes, I can hear you.
Please talk about the on edge on the UE side, which has to integrate into the, let's say, base station. Let's make it very simple. On the 6G side, I want to ignore the AI on the base station side. I want to concentrate primarily, and that's what I'm teaching right now in school. So could you please elaborate on that?
Yes, this is a actually very key question. Because of AI fundamentally is built on the so-called large language model. So human level of intelligence, actually everybody brain has a 100 trillion of coefficients. So in the case of semiconductor progress on the device, 2030 maybe 100 billion. So 100 billion is the intelligence even less than the house mouse. So to deliver human intelligence to everybody, everywhere, anytime, you need to talk through the network, go through the data center with a human brain like large model, let's say. So network is a necessary step. You cannot skip. Now your question is this: what is the edge? So in terms of the edge is more important because if you want AI take actions for you, do things for you, for example, to cook for you, or the robot to do anything, you have latency constraint. You are not able to get a service from Google in California and then answer back to the Istanbul to help you, your robot to do the thing. So there must be some edge computing in order to get that intelligence level. I'm not sure, I made the thing clear. So in that case, and the third part is because with all this AI, data is the most precious resource. You have more data, you will have even become more intelligence. That's the story of all the large language model. So nobody want to give up data. So most of computing has to be in the local, even better in your device, own device. That's what I'm trying to tell you how this is a partition.
I'm not concerned about cooking in the US, for instance, to get me a response back on the UE. I'm more concerned about autonomous driving, for instance.
Yes.
Or driverless driving.
Yes.
You need a real-time data computated.
So then that must be edge or even on device.
Is Huawei working on that?
Yes, of course. Well, by the way, we sell the autonomous driving car already. Like per month, 10,000 or no, I forget the number. It's 100,000 car per month that's produced. Yeah, it's a fully level 4 autonomous driving car.
Yeah, thank you for the amazing talk. This is Abdülkadir Çelik from Coast. I'm here, yes. So I see that sensing is also one of the key words that you are repeating in your slides. And by sensing and also referring to the autonomous vehicles, most probably you're referring to multimodal sensing, right? Including cameras, LiDARs, GPS, and all form of sensor modalities. So 6G networks will not just convey them, but also process them and also utilize them. And where it will connect us to digital twin concept and etc. But at this point, I also do research on using LLM for this multimodality and sensing and perception, environmental perception. But at that point, you also are referring to different models for different jobs at different levels. So do we really need very large language models, or shall we scale them depending on the computational power available at the edge devices or servers, or throughout the hierarchy of the cloud system? Thank you.
Yeah, thank you. So because of the architecture, there are some hierarchical things. I have 4 agents. Each agent has a model. Maybe this model is a common or maybe are different. And that model may not as complex as a ChatGPT model, but that model has to be domain-specific, fine-tuned. So because it do certain specific job they need to do. For the sensing part, I want to just repeat because this is my opportunity. It's very important for the data to collect it, to do the sensing. Therefore, AI can understand the true physical world. So far, all this model today, they are not understanding the physical world. So they are all, the other aspect is the AI model today, it's all exhausted the internet text that we produced. However, a 4-month-old children, if they don't sleep, the input of the whole information from visual is the summation of an entire human being text. So that means the visual or the physical world or the spatial world is more rich or important from the data in order to make AI to work for us.
Any further question? No? Okay. All right. Let's thank our speaker one more time.
We would like to thank dear Dr. Tong for his inspiring speech. We are inviting dear Professor Hüseyin Arslan to the stage to present his gift.
At first, many thanks to the organizer, Hossein, and thanks a lot for your invitation, ZTE Corporation, to come here to share our innovation research progress with Turkish academias, industry, and also institutes. So thanks again. And today, my report, the title is What Will Make 6G Different? And my report just, yeah, thank you. Okay, my report is just 3 sections. Section 1 is just a simple introduction for the 6G scenarios and also roadmap, just mentioned by some speakers. And the second section is about what's the real technical challenges from 6G. And the third section, we just share our initial trials towards 6G. So, for section 1, and these 2 figures is just describe what's the 6G network scenarios and KPI requirements. Just now, some speakers just show the left figures. I don't mention again because it's a typical 6 scenarios. And new scenarios just compared with 5G. And also some enhanced 3 scenarios as compared with 3G. But we need to care about capabilities of 6G. On the right hand, we have green parameters. That's the enhancement performance of 5G, such as peak data rate and and also user experience, data, latency, and device connectivity density a lot. But at the same time, we have to mention new capabilities in blue color as compared with 5G, such as coverage, intelligence, sensing, and also sustainability, interoperability, like that. Of course, the positioning is also another new capability supported by 6G. So, in this way, that means 6G has different scenarios and also different capabilities as compared with 5G and even 5G evolution. That's called 5G advanced. And okay, maybe you want to ask, what's the typical user case of 6G? Here, this slide just shows some example. For example, the digital twin and immersive cloud XR, holographic communication, sensory interaction, and also human augmentation. Because for 5G, we only care about voice and also video. That means the C side. And in the 6G, we need to care about other senses of human body, such as touch, taste, like that. So that can enhance our human capability of that. As well, we such as precision medicine and logistic e-drones, global coverage, and covert control, and remote e-driving. So that's the typical user case for 6G. How about the 6G development roadmap? And this figure, just a summary of the major steps that we need to finish in future 5 and 6 years just for the deployment of 6G network. For the blue part, it's ITU guidance for requirements and also for evaluation of candidate specification. So ITU doesn't specify the 6G standards, it's just raise the requirements. And who will finish, such as 3GPP, that's a standard development organization. The green color just mentioned that for release 21, that means it will should be the first 6G standardized specification will be completed from 2026 until 2028. And then the 6G phase 2 should be finished from 2028 until 2030. So before that, we need to finish the requirement specification, and then the L interface feasibility study like that in the release 19 and 20. So that's the major roadmap for 6G standard development. And then how about the 6G technical challenges? This figure is just a summary of all the major 6G technologies. And for the green side, it's a kind of evolution technologies. For the blue side, it's disruptive technologies. So, for example, flexible spectrum utilization and beyond the MIMO degree of freedom and the higher band extension and integrated non-terrestrial network and the terrestrial network. And at the same time, almost every expert here mentioned AI. So the new technology such as AI native network and AI native L interface, that's a totally disruptive technology. At the same time, integrated sensing and communication, as well as integrated powering and communication. Why? Because besides sensing, we need to support a lot of IoT devices. But you know, some IoT devices couldn't support long-term battery. And also, how to say, it's very ubiquitous and deployed in a wide place. In that place, you cannot find the people to replace the battery for it, right? You cannot find the power supply to connect for the ubiquitous IoT devices. So in this case, the network can do something. That means it can support the wireless powering for the IoT devices. So that's give more flexibility for the device deployment and also for the sensor application. So for these key technologies, I think you know some new technologies such as backscatter communication, that's wireless support, wireless charging from network to the sensor side. So we think this key technology should be studied in long term, not only for 6G, but also for 6G advanced and also afterwards for that. And of course, the new network architecture. That means network native as a service architecture. And all of these 8 bullets, it's the major technology building block, but it's not enough. We need to support from the L interface side. It's the bottom line. We need to support sustainable for L interface, such as advanced modulation, channel coding, waveform, and multiple access, duplex, antenna, and optical wireless. A lot of technologies to be resolved not only by vendors, but also by the academias and the institutes together. Of course, the first bullet is just mention the end-to-end technologies, such as intent-driven, cellular AI-based API, distributed topology, device-side cloud computing, just mentioned by the professor, and also customized assurance and digital twin. So there are so many challenges or key technologies we need to give the solutions. How about the architecture? And this slide just show what's the architecture evolution from 5G advanced to 6G and even 6G advanced. So for the green side, it's the 5G already deployed in China and also some other countries. And for the blue side, blue blocks, it's 6G technology. For example, for the spectrum, the blue one, it's new mid-band. That's range from 6 until 15 gigahertz. So some people mention as a centimeter wave. And also the new high band, that means above 100 gigahertz until 300 gigahertz. So all of this new spectrum resource should be supported step by step. In my understanding, for 6G phase 1, it should support new mid-band, such as up 6 gigahertz, already, already agreed as the IMT spectrum. That means it has a wide bandwidth over 400 megahertz and even 500 megahertz like that. And for 6G phase 2, it should support new high band. So the technology should be evolved step by step, and no time to mention in details. Okay, because now, today, we have many professors and also graduate and also the PhD candidates. So this slide just to show our some points to call for open innovation from a collaboration of academia and industry and the government together. So what's the breakthrough technologies towards future L interface? This figure just gave the major 4 kinds of L interface. For example, the first one is terabit per second MIMO. That can support even 48 and even 100 parallel streams. So in this case, the spectrum efficiency should be greater, much more than 5G. So this is the number 1 breakthrough challenge. Number 2 is sensing, but it's not by AI. It's not by fixed signals. It's by radio frequency signals. But how to support? The L interface of RF imaging, that means the resolution should be less than the half wavelength. Why? Because we know for the spectrum, I give some typical number. For example, for the centimeter wave, that means 10 gigahertz, for example, then the half wavelength is 1.5 centimeter. So because by using the conventional sensing technologies, the most accurate resolution is half of wavelength. So that means 1.5 centimeter. Can you imagine how to classify the phase of human, 1.5 centimeter, no. For example, for the eyes, mouth, nose, you cannot identify who is this guy. So in RF sensing resolution, it's not enough. That means I have to say frankly, that means we, even for 6G, we have already met the science bottom or science border for that. So it's a real science problem for that. If we want to use RF signal or wireless signal to support high resolution and high accuracy and high reliable sensing of the environment and the human, and also some many objects. No, by using conventional technology, you cannot, because now it's a science border for that. So how to do? We have to introduce scientific innovation to support RF imaging that's much more less than half wavelength. Then you can get the capability of light sensing, right? Of the camera sensing. If not, cannot for that. So that's the second breakthrough challenge for that. And the third one is AI native L interface. And this morning, I remember a professor already mentioned what's the problem. The problem is energy consumption and the energy efficiency. For that, so we need more breakthrough innovation for energy effective AI native L interface. So that's the third breakthrough challenge. And the final one, I just mentioned the RF powered wireless charging for that. So the key problem is the energy efficiency. It should be greater than 60%. That's a very challenging science problem we need to resolve. So in this way, we have to be, to be clear what's the science problem or science issues that should be resolved before the large-scale deployment of 6G, before the complement of 6G standards. So just following, synchronized with this morning's professor's question, we don't have, so many years. We just only have 5 or 6 years to do this kind of breakthrough innovations. So it's more challenging than the legacy generation. And here, this slide just shows the rank as a service for future wireless channel. Because the left red circle is just a summary of all the major design elements of antenna array, such as the spacing of elements and the deployment architecture, distributed or centralized, and evanescent wave. I think many professors know that, and because it's very near. And also the reciprocity, metamaterial, and the polarization. And on the right hand, we have some candidate new technology for MIMO evolution or MIMO innovation, such as distributed MIMO, multi-user MIMO, and the super resolution MIMO, and the super directive list large intelligent service, and the flexible or full duplex, and lens MIMO or wrist-assisted MIMO for that. And the final one is multiple polarization. Because as you know, the conventional polarization is just 2. right? And we cannot support more than 2, such as 3, 4, 5, 6. And as you know, if we, for example, if we can support a 3 or 4 polarization pattern, then the spectrum efficiency should be 1.5 and even 2 times directly. So this technology is very, very cost-effective innovation for that. And just combining the design of different elements of the antenna and also different new candidate technology, we need to introduce physics-inspired innovations for rank as a service. And how about target? I just mentioned. For example, in medium term, it should be greater than 48 streams. And for long term, we need to decouple the capacity and energy. In this case, we can support the energy effective 6G and even 6G advanced. If we don't find such kind of breakthrough innovations, no. The energy efficiency 10 times than 5G, and also for AI and for sensing, no, cannot be supported. So that's our, understanding for the rank as a service for future network. And for the net AI, how about the challenges? A lot. And the left figure is just to show the conventional for 5G and even for 5G advanced network AI, such as some user case for energy saving, for the load balance, mobility optimization, and the modulation. And as well as for MIMO feedback, channel estimation, and RX equalization, and also for the demodularization. So that's the traditional communication model that supported AI technology introduction. But it's not enough. We need to support one model, many scenarios and tasks. That means in the network, even in 5G and also 6G network, we have so many functions, network functions. Can you imagine one network function by using one network AI model? No, we cannot do that. We need to support one model, many scenarios, and tasks. In this case, we can significantly reduce the network complexity and also downloaded by device and also by app applications like that. So it should GPT or transformer based large model, but large is not enough. We need to support at the same time the frugal intelligence for that. So we think large but frugal is different. So we have so many challenges to be resolved. Also, of course, we need to support responsible and collaborative AI or ML for that. But I think no time to mention one by one. And so in long-term evolution, AI should be introduced phase by phase. For example, first time it's AI for network function, and then it's AI for network, network for AI. And the final, it's a network AI generated new network function and an even new application. So we have many steps for the intelligent network. Okay, Section 3, we just show some initial trials towards 6G. Here, this is our initial trials on 6G technologies. The first one is integrated sensing and communication, such as densimeter positioning and the dynamic tracking of moving objects like that. And the second one is base station and wreath co-beamforming. And in this case, it can support multi-user 2 times throughput. And the third one is multi-scenario real-time terahertz, new high band. And width, that should, new high band, terahertz bandwidth is very large. It's not enough. We also need to support high spectrum efficiency, such as greater than 10 terabit per second per hertz, like that. And the fourth one is wireless AI. That means we use AI transmitter or transceiver to get 10% throughput growth. This is an early trial for that. And also the RAN together with a core network, computing network, and a data service with data orchestration, control, and forwarding, like that. And all of these trials is organized by the Chinese IMT 2030 promotion group. That's a government institute organization for that. And okay, this is some case, a detailed case. This case is for Assoc. It's multi-station networking in Guangzhou, you know, the very big city, super city in China. We finished the test. The test requirement it's children's park in Guangzhou city, and the test equipment is a millimeter wave base station working on 26 gigahertz. Bandwidth is only 100 megahertz, and the sensing mode is monostatic. And test result, we can support seamless sensing within 300,000 square meter region. And the sensing accuracy is less than 1 meter. And the sensing target is support simultaneous sensing of multiple target. And for this one, we just mentioned it's a millimeter wave ISAC. This is a sub 6 gigahertz ISAC. And it's 4.9 gigahertz. That's allocated to China Mobile. And the bandwidth is also 100 megahertz, and the sensing mode and the networking of 2 sites deployed on the route. The red line is the target moving route, and we have 2 sites just follow to sense its track. And for the distance accuracy, it's only 0.2 meter, and moving speed is can be accurate for 1 meter per second, and for the direction, it can be can reach 0.3 degrees of that. And okay, for sensing of a vehicle, the first one is for drone, and the second one is for vehicle. Almost the same speed, but different how to say, direction, and also the distance accuracy. And okay, this is the trial for the wreath application in the 19th Asian Games in Hangzhou in 2022, in the year of 2022. And by using the race panel, we can support the performance enhancement such as average downlink data rate, uplink data rate, and RSRP strength, and also the signal to noise ratio enhancement of that. So it's a kind it's industry first dynamic race operation of that. Okay, this is a base station assisted race dynamic control with terminal feedback. And then you can find, how to say, the base station and also the race deployed like this. And test case, how to say, it can support multi-user MIMO like that. And for beam steering, its average RSRP increased by 20 dBs. And also for MU MIMO, downlink speed is 3.3 gigabit per second by 2 layers. And also the coverage distance is large for over 100 meters, like that. And okay, this is a self-healing beamforming. Unlocks high band unloss, that means non-loss transmission. As you know, for millimeter wave and also for sub-terahertz wave, the wavelength is very, very small. And penetration loss is very high. And the wave, electronic magnetic wave in high band, that is very sensitive to blocking loss. So how to resolve? That's the traditional problems already met by high band, include not only millimeter wave, but also for terahertz like that. So how to do? And we do some trials against non-loss blockage. So in this case, if we don't introduce self-healing beamforming, then even for millimeter wave communication sensing, you can not overcome the impact of loss blockings. For example, for this table, millimeter wave come here. If my mobile is here, no block. And even for human body, if this is my mobile and this is a base station on the roof, come here, if, how to say, stop by my head, it should be, blocked by the obstacles, because the obstacle's size is larger than the wavelength. How to do in this case? That means it's a shadowing effect, shadowing fading of high band signals by some indoor and outdoor obstacles. So in this case, we find that physics-inspired self-healing beamforming can contribute to some solution for that. That means it can support base station native non-loss propagation against environment and human body blocking. The left hand is the simulation for the conventional beamforming. You can find in the middle here is shadowing fading, shadowing fading. This is an obstacle. But by using self-healing beamforming, it's okay. But this is only simulation results. We have also some trial, not only for millimeter wave, but also for sub-terahertz. The trial results is that it can support non-loss enhancement by from 6 until 10 dBs. And also for self-healing range, we trial, the range is around from 0.18 meter until 20 meter. That means in future, if we introduce the high band, such as sub-terahertz for wide bandwidth, and then almost everyone here can have, very super data throughput sphere around you. And that any obstacles can be, can be reduced by the self-healing beamforming of that. So that's our new trials, just be going together with China Mobile. Okay, a summary. We have so what will make 6G different? I think number one is new scenarios that make 6G different, but it's not enough. We need breakthrough innovations, such as the four blue L interface, terabit per second MIMO, AI software, AI-based software-defined radio, and the super resolution L interface I just mentioned for RF imaging or RF sensing. That's over the half wavelength limit of that. And also the super reliable L interface, such as I just mentioned, the self-healing beamforming to increase the wireless reliability of that. So both the new scenarios and the breakthrough innovations will make 6G different. Thank you very much.
Dr. Fang, thank you very much. It was a wonderful presentation. I'm sure we have a lot of questions, actually. You made a lot of statements, interesting statements. I can take one question because we need to move on. I have a question, actually, a quick one. I think you were in Eric Dahlmann's presentation, right, this morning? Dr. Dahlmann's presentation.
Yeah.
So he made a statement that even if we are not ready for 6G, we have to move on. Whatever we have in our hand, we have to start 6G. And in your presentation, I also realized that we have a lot of scientific tasks that we need to achieve. It looks like we are not ready for 6G. Do we have to move on?
Yes. I think that's the time, time is, in general, is not enough. But in another way, it's also okay for 6G, because I just mentioned the breakthrough technologies. We, by the collaboration of industry and the university, we already find some, some new format or new pattern of candidate technologies to reach that. For example, super resolution, and also for the for the super degree of freedom, like that. So if we can introduce, because now the open innovation is totally different with the past. Now, we try to make some open innovation together with university, and then to push into 5G advanced application first. So in this time, if 5G advanced is okay, for 6G is also okay for that. Okay. So the iteration rate is more fast than before. That's the different innovation style of that.
Okay, so you're saying we are ready?
It's not so completely ready, but it's
almost ready.
Halfway ready. Okay. So we still have 5 years to finish another half for that.
All right. Evren, quick one. There is a mic over
there. Hello, Fang. Thanks for the great presentation. My question is about AI native energy efficiency of 5 layer. So when we think about the energy efficiency, we apply distributed learning, federated learning, and even transfer learning. And we are talking about collaborative training. And we are trying to balance the accuracy and complexity. So can we apply any other alternatives to increase this efficiency? What is the point of view of ZTE?
What's the point for?
Can we apply any other alternative ways of increasing the efficiency in addition to existing ones?
So I think for the collaboration intelligence, the key problem is that the data cover, the data set should be located in the local place. And if we try to share or transmit the data set from different locations, that means the energy consumption will be a great deal of that, and at the same time against the regulation, right? So in this case, local data set for local processing is very important. That's the key problem and also the key solution of collaboration AI, the first one, number one. But for this one, it's not enough because just now there is a professor who asked about the edge intelligence, but only edge intelligence is not enough. We need the collaboration not only for the local data set, but also for local intelligence at the device side, and also the local network intelligence at the edge side. And also, if some data just near the data center, also we need the local intelligence from the data center. So the second issue or solution is for the collaboration learning or collaboration intelligence by local model, as well as the collaboration model from data center, from the cloud, from the edge, that means the base station, and also from the device side together. But I already just mentioned, we cannot support, it's too luxury, many models in parallel. We need, one model, but it's a collaboration, one model from different vendors and also from different locations, just to, resolve many tasks in parallel, but it should be support frugal intelligence of that. So in this case, that means we can reduce the energy consumption just from the view of one task, can reduce the energy consumption in a great degree. But if we, from the view of many tasks in parallel, so it's a network collaboration intelligence, not only by the AI model, but also for data set together. So that's my understanding for that. Thank you for your question.
Thank you.
Okay, all right. I think we need to move on. Dr. Fang, thank you very much. It was a really wonderful presentation. So we are going to have a gift for you before you leave. Are you going to be around during the break? During the break? Okay, so if there is some further questions, you can ask Dr. Fang during the break. So I'm going to ask our next speaker to give the gift female to female, Çiçek Hocam, for our speaker, Dr. Fang. So there is a gift, Dr. Fang, for you. Yeah, there is a gift for you. So, okay, all right. So in the meanwhile, I'm going to also introduce. Yeah, go ahead. Yeah. Çavdar. Okay, thank you again. Our next speaker is the one actually who is presenting the gift. my friend, we are collaborating with her as well, Çiçek Çavdar from KTH. She has been doing a lot of great work and a lot of European projects, and I'm looking forward to hear also her perspective of 6G.
Hello, everyone. Thank you so much for the kind introduction and inviting me here and organizing this workshop, dear Professor Hüseyin Aslan. This is my really pleasure to be back to Istanbul, my city, after 6 years, thanks to this event also. And with many of you, we have been collaborating in different projects last 10 years in EU projects. I see many familiar faces, and it's great to meet up again in this venue. You know me mostly with my research in green communications in general, and projects like AI for Green, 6Green, and so on. This one is another project, it's 6G for Connected Sky, 6G Sky. Here I would like to talk about the integration of terrestrial and non-terrestrial networks under the frame of 6G. So this talk is not about satellite communications. It's been a very big topic since like so many years, but I will mostly focus on the LEO satellites, its integration, and also flying users, flying vehicles, how to support connectivity of those critical command and control links for those users. So where are we in the evolution of non-terrestrial network and terrestrial network integration? We have actually here 3 elements in 6G Sky. One is satellite, the other is terrestrial network, and we have also airborne networks where we have like UAVs, flying taxis, passenger aircrafts, as you can imagine. And here, interconnected heterogeneous networks are today, actually where we are today mainly. In that case, we have been designing and optimizing those networks independently and exclusively for terrestrial networks so far. But with the new projects last few years, we started also looking into the integrated design of these 3 different network segments. So we then started designing and optimizing those integrated networks, mainly focusing on the terrestrial network component. So we wanted to basically aim for the terrestrial networks and start expanding the coverage and availability of the terrestrial networks by using non-terrestrial networks or by using hubs type of links. We are now, with these new EU projects, we are somewhere in the middle, mostly still struggling with this integrated design. With 3GPP standardization also there has been a lot of work going on, but still directly connecting from my mobile device directly to the satellite, where are we? We are like in 2G level, you know, we can't communicate properly, we can only send some SMS messages directly from our phones to the satellites. So we still need special terminals. And in the future, we are like aiming for a single unified network where we want to design and optimize network resources for both terrestrial and space components, and against a set of common goals. And looking into the 3GPP and standardization, this story started with Release 17, first non-terrestrial network 5G NR and NTN narrowband IoT has been developed in the standards for FR1 in general. And then it's continued with Release 18, enhancements with the addition of FR2. And now with release 19, further enhancements are going on, looking into both FR1 and FR2 for regenerative scenarios. And so far it was only expanding terrestrial networks with some compensation with the Doppler shift and so on type of challenges. But now new architectures is going to be studied. It has already started in release 19. So this is the big picture. I just wanted to draw the big picture, and now looking into our project more specifically. Who are we? I was the technical scientific coordinator of this project, and the project manager is actually Tele2 in Sweden, and Airbus actually the main coordinator from Germany. We have Austria, Germany, Hungary, and Sweden here. And we have 15 partners. And we have also Ericsson contributing heavily in this project from different countries, Sweden, Hungary, Germany. And we have a SAS flight operator also. And Deutsche Telekom. As you know, Deutsche Telekom is the operator of the European aviation network, where they are kind of holistically harmonizing the direct air-to-ground communications in countries in Europe to provide direct air-to-ground communication to flying vehicles like passenger aircrafts, for example, flying at 11, 13 kilometers. And this project started beginning of 2022, and now we are going to end in a few months. So the goals that we were focusing on was about mostly under three groups: reliable connectivity for both aerial and ground users. There we were aiming for flexible and adaptive network architecture, multiple types of links, and multi-connectivity. And the second objective has been 3D network design and management, focusing on aerial vehicles with differing requirements, like passenger aircrafts with a lot of data throughput requirement, or critical communications with drones or flying taxis. And the third area was non-terrestrial network for ground users, where the first thing was coverage for rural areas without infrastructure. This has been a very wide, area for some time already, with remote IoT, for example, connecting remote IoT directly to the satellite, and augmented networks for urban areas also. And in the project, this was the first project in Europe looking into this topic. Then a lot of projects started afterwards. Here, our strength is we were very lucky to bring together all the kind of stakeholders in this value chain and able to collaborate with all of them. We had the suppliers, operators, users of all this kind of technology. Starting with the SAS mobile airplane operator and network operator like Deutsche Telekom, and we had system vendor like Ericsson, Airbus as the aircraft vendor. So it was really bringing together a lot of strong stakeholders in Europe. We were focusing on two use case segments and scenarios under two groups. One is airspace communications, what we call commercial aviation, advanced air mobility. Advanced air mobility is mainly focusing on smart transportation of goods and people, for example, through drones and flying taxis, smart city services, smart logistics, and verticals beyond the AM, air traffic management systems. And the second area was about non-terrestrial networks, connectivity for rural and remote areas, how to provide connectivity through the non-terrestrial networks to those remote areas. Non-terrestrial network backhauling of non-3GPP services in disaster management scenarios, for example, and Internet of Things, directly connecting to the satellites. Now I will just walk through our different topics, use cases. Before we walk through the 3 different use cases, I would like to talk about the main system architecture and resource orchestration framework that we developed. And here you can see what type of links that we are dealing with. Inter-satellite links, air-to-air links between different flying vehicles, direct satellite to terminal links used as backhaul or user device, and also links supporting, let's say, UAVs, for example. Here you can see one UAV connected through both satellite plus base station, terrestrial base station, and also side link, air-to-air links, which was a main topic in this project where we were aiming for very high reliability. And looking into the network orchestration, we were aiming for actually, with the assumption that we have processing in the satellites, LEO satellites, and with another assumption that we had also inter-satellite links enabled. We were looking into the ORAN, Open RAN, and the segregated RAN into the LEO satellites, like on these flying networks. Then, as you see these colored boxes, don't know how to point out, on the left, red and greenish, you see the RUs, radio units, DUs, distributed units, and centralized unit in this disaggregated RAN, where you can separate the baseband processing from the radio, and you can place those pieces at different parts of the network. Basically, it could be a flying node, it could be a ground station in the network, and so on. And here you can see different nodes with different abilities. We had different terminals also. And how to combine all this together in a single architecture was the main challenge. And you see our main use cases here at the top: urban air mobility, commercial airplane, digital airspace management, where we have command and control links, like remote piloting of those like flying vehicles, and rural coverage. It's a very different, actually, communication system, which requires. But all these different requirements have to be met with a single network architecture. So this architecture requires really flexibility. Flexible allocation of these resources should be enabled. So we need to build on top of the 5G network slicing, and also plus we would need to go further with the ORAN abilities, which is providing a lot of flexibility to us. So looking into very basics, evolution of architectures and satellite communications, first you see here on the top, here, transparent architecture, where satellites act as a relay node. So all baseband processing and RAN functions are placed on the ground. So this satellite has no processing, no intelligence. Actually, it's just relaying the communication signals to the both ways. And now, with the advancement of second generation satellites, regenerative architecture is possible. Satellites have some onboard processing capabilities. So part of the baseband processing and RAN functions can be placed on the satellite, where you see on the right. But this brings a lot of advantages, but also together some challenges. So our first study was looking into this flexibility. Are we really capable of like adaptively play with this, like different network function processing elements and place them at different parts of this network? Because the distances are very different than the ground networks that we used to work with. As you see here on the left, we were looking into the flexibility of different network function splitting between the gateway, ground station, and the satellite. So as you see at split 10 on the right table, if you look at the table on the right. These are the function split options, 1, 2, 3, up to 10. And there you see, for example, 10 is the case where basically you put all G naught B almost on the satellite. So where we require a lot of bandwidth on the frontal link, that means the feeder link that you see on the left, which is not basically feasible. Typical CRAN is not feasible. There. And the second ninth, I'm going from bottom to the top. The ninth is the low layer phi split, where we keep some of the low layer physical layer functions at the satellite and put all the rest on the ground station, where this requirement goes a little bit down, but still a lot. So as you see, go like this until the first split, the requirements in the frontal link, this feeder link, changes drastically. And we studied the practicalities of this, feasibility of these different splits, basically, in one of our papers. For example, in satellites, in order to enable this physical layer split, where we actually save energy on the satellite by moving most of the physical layer functions on the ground station, and we can basically save energy. We see that it is not possible except we modify the physical layer a little bit. For example, disabling the HARC feature completely. Then we can relax frontal latency in the new radio non-terrestrial network. Or CSI reporting or reciprocity channel-based estimation feature, which requires a very short delay and may be disabled also to relax this frontal latency. So we need to adapt and modify actually some of the physical layer elements to be able to move on to these flexible splits in the sky. And another challenge here is when a handover happens, a user is handing over from one base station to another. Here on the left, the satellite is the same, but beams are different. And in the middle, you see that base station is moving from, user is moving from one base station to another base station. So both base stations are different in this handover process, but their ground station, the ground station is here in this 2D picture sitting on the top. It's not flying, it's in the ground. So it's just a drawing trick. So this ground station on the top is connected to two satellites where a handover is happening. And on the rightmost figure, you see that also these two satellites can practically connect to different ground stations. And imagine that these are moving. So as these are moving, handover process becomes very complicated. If you split, let's say, from a low layer, if you use a low layer split, basically, then you have to start processing the in one ground station, and then you need to transform this processing on another ground station if you are basically handing over. So this brings a lot of complexity based on which split that you are choosing. The handover process needs to be fully updated, basically. So here again, our observation was this low layer split LLS option minimizes satellite computational demands, reducing power consumption and payload. And on the other hand, full G naught B on board satellites, this relaxes bandwidth and delay constraints, extending coverage but increasing the CPU and payload complexity, which might be a problem on the satellite. Another feature in the 6G Sky project, another challenge that we were dealing with, it was multi-technology connectivity links, where we were here focusing on, let's say, remotely piloted aerial vehicle you see in the middle. And there, for this remote piloting, we need very high reliability, like 5.9 reliability is required. So it's very hard to continuously provide this through direct air-to-ground links. So we were considering here the usage of multi-technology, like hubs to UAV, satellite to UAV, direct air-to-ground, terrestrial base station to UAV, and all the combinations of this, we were developing some end-to-end delay models and end-to-end path, considering the path reliability also. And asking the question, trying to answer the research question, do we really need all these links? I mean, and what distances and what conditions we need to connect to all these different technologies? And here first, I will talk about this first use case, advanced air mobility, reliability and continuous availability. How to actually, we started this work by some measurements done by my colleague in KTH. We did some drive tests, basically. On top of the car, we mounted some Starlink modem. And we had also TEMS equipment measuring 2G, 3G, 4G, 5G connectivity. And they were driving up to the north of Sweden to see, like, how is the coverage? I mean, in the remote areas, how is the coverage? And can we improve this coverage, basically, by Starlink or by multi-connectivity? And as you see in the table, if you look at the access technologies, we looked into Starlink, cellular, and Starlink plus cellular. So if you look into first percentile users, Starlink, those users, worst case users, Starlink wasn't able to cover them, but cellular was 0.54%, was able to, 0.54 Mbps was provided by cellular for this worst case 1 percentile. And if we look at both links, joint communication, we were able to provide 8.42 Mbps. We were using a special modem, actually combining these technologies from a company like iComera. And in the second 5 percentile, you see 12.9 was available by Starlink, and then like this. Here, the interesting thing is the worst case user, 1 percentile users. With Starlink, you are not capable of covering them, of course. And also with cellular, you are very bad, like 0.54. But with both of them, actually, you can really increase 8.4 Mbps. And this is important, like in terms of continuous connectivity, which showed us even in the very north of Sweden, in the Arctic Circle, you can basically cover those users in remote areas if you support this cellular with the LEO satellites. So with these observations, we kept working on this topic, actually, and developed models, as I have mentioned earlier. And we demonstrated that a combination of all the routes, actually, coordinated multi-point plus air-to-air links plus hub and satellite K-band, is able to ensure the target reliability of 5 nines, considering today's kind of networks. Like we were considering also the backhaul connectivity, end-to-end reliability model here, for a special case of command and control links, where decoding error probability was an issue in the for the radio access link, actually. The second, we continued with learning-based dynamic cluster reconfiguration for these flying vehicles, mobility management with 3D beamforming. There we were looking into this providing continuous reliability for these UAVs and managing the mobility. So in the traditional mobility management, you basically connect to a single access point and then move to another access point and another one. Here we were looking into a clustering topic, like you are served by a cluster of base stations, access points, and as you are moving, this cluster needs to be reconfigured. An access point being far away should be dropped and the new access point should be added into the cluster. So this is very different than a typical handover mechanism, and you have to do this cluster reconfiguration. and continuously with for multiple flying vehicles actually, also to avoid clashes. So here, this problem is quite complex. So we used basically some machine learning algorithms here. And here we were minimizing the power usage and reducing the frequency of cluster reconfiguration. So we don't want to keep like updating this cluster again and again and very frequently. So that was the goal here. In use case 2, we were focusing on LEO and UAV multi-layer connectivity for Internet of Remote Things. Here, the main idea is you have sensors in a very remote area. You are collecting some data, and you don't have any infrastructure to basically upload this information. And here, we were using UAVs to help those like battery-powered devices, which power is a limited, basically, asset. So we were basically collecting the first data from those sensors through the UAVs, and then UAVs were transferring this data to the LEO satellites. Here, the problem is LEO satellites are, that link is fluctuating. That link is like going down and up, and this fluctuation can be high depending on which satellite constellation that you are using. Sometimes it can really go down if you are using, if you are like based in somewhere in the north and you don't have that many satellites basically orbiting on top of you. In that case, the UAV needs to be really smart. I mean, you need to wait when this link becomes available and strong. You should then transmit to the satellite. You shouldn't try to transmit all the time. And also, this UAV needs to be smart to move around those IoT sensors, collecting the data, and decide on when to cache, where to cache, whether to transmit or whether to cache this data until the right time. So you see the publication for the details. You can check those. And the third use case is AI-assisted LEO satellites handover management for coexisting aerial and terrestrial UEs. Here, the main problem was handover management through the satellites. As LEO satellites are moving, they are basically moving with 7.8 kilometer per second speed. It's very high speed, it could be. So the user in the ground has to kind of adapt to these earth moving beams. So beams are moving. So how to, this is one thing. And another thing is to decide on which user to serve by which satellite. Because if you look at the Starlink constellation, somewhere in Europe, like Turkey, although this connectivity is disabled now in Turkey, you can see multiple satellites, even up to 10 at a time, and you need to choose which one to connect. And also the area is quite large, and there are a lot of overlaps in those kind of beams. So it's an interesting decision to make which user to serve by which satellite with a minimum number of handovers again, and guaranteeing a certain service requirement, considering the load coming from different users also. So that was the study here. We were focusing on a scenario like in Stockholm and a realistic satellite constellation. We developed a simulation environment where we have all the Starlink basically satellites and links modeled and all this. And we were using some traffic distribution models for airplanes, UAVs, and also terrestrial users. So we had different type of users that we need to allocate. So the goal was minimizing number of handovers with a guaranteed requirements from different set of users. So here the decision-making mechanism was challenging. So we focused on an RL algorithm called Nash Soft Actor Critic. It includes actually a maximum entropy framework that encourages the agent to learn a more diverse policy by explicitly maximizing the entropy of the policy. And the combined MIRL and Q-learning with the general sum K-agent game was helping us actually to find optimal equilibrium policy when each agent gets the maximum expected rewards, basically. So we had this framework guaranteeing us to basically converging to an optimal handover mechanism. So, and compared with like best signal approach or lowest loaded kind of LEO satellite approach, we were really minimizing a lot the number of handovers, around 74%, and also guaranteeing the certain requirement from different users. This is some walkthrough in our 6G Sky project. Now I will a little bit, in 1 minute I'll talk about the demonstrations. What are we aiming to demonstrate at the end of the project, since we are kind of approaching. First, we actually aim for lab emulations to demonstrate this satellite, airplane, and the connectivity on the left, to assess the link benchmarks at Fraunhofer. The second, we are aiming seamless connectivity via multiple links. Actually, that is the most challenging case, where we want to connect airplane or like a kind of very high, let's say, drone, altitude drone, not an airplane, flying on top of Airbus Ottobrunn, where the fast flying vehicle need to connect through different multiple links. We have satellite connection available, and we are looking into direct air-to-ground connection, and kind of combining these in a real test bed, and switching between these two as the UAV is moving. And the third is drone swarms supporting goods mobility. It's a use case in Austria, where we have, let's say, around 10 drones that we are swarming, and they are kind of load balancing, using some of our load balancing algorithms. We want to test this mesh connectivity between these drone swarms. The fourth demonstrator is about drone sense and avoid mechanisms. It's going to be in Kista, Stockholm. It's a collaboration between KTH and a small company. There we are using sensors, receivers, to sense unauthorized drones coming into the air. Basically, we are trying to track the signals coming from those drones and sense where they are. And the fifth one is hub connectivity. We are focusing on Deutsche Telekom actually set up there, where they are trying to integrate this hub into their existing terrestrial network. There we are aiming actually to even try FR3 bands. So after this one, our 6G Sky project will be finished. And with this, this is the team preparing demonstrations. And this is the end of my talk. Yes,
okay. So
maybe I should be asking if you have questions.
So I took over the moderator role from Hüseyin Hocam. So I think we have time for one or two quick questions to Çiçek Hocam. Thank you, Çiçek Hocam, for this inspiring talk. So as far as I see, many partners directly working in the field are directly collaborating on this very important topic for future wireless networks. So we can have one or two quick questions to Çiçek Hocam. Any questions? One at the back, very back.
Hello there. Thank you for your presentation. I have a question regarding NTN in general. The technology that you presented looks very promising, but I gotta ask, is it backwards compatible with already existing satellite constellations, like the one with Starlink, the Elon Musk company presented? Or, as in, my question is, does it require a new infrastructure to be implemented, or is it backwards compatible with already existing infrastructure in order to actually achieve it with the requirements of 6G?
Yeah. For example, Starlink is a separate network, totally like following other type of communication system protocols. They are not following 3GPP. But it would be actually a software upgrade if they want to follow 3GPP. So all satellite operators, they could follow the 3GPP standards based on their choice. I mean, in that sense, I mean, backward compatibility is maybe not the right question to me, but maybe we should ask, like, who is going to follow the standards, like, or who won't be following the standards and they will choose to just provide their kind of independent system where it will require independent terminals. Then you can't communicate with your mobile phones. You have to buy, for example, today in Starlink, you have to buy this special terminals to connect, and these are quite complicated and devices you can't carry like a mobile phone. So the goal here is, I mean, still the same constellation, the same satellite would work if they implement these protocols of the 3GPP. With some very simple modifications, for example, compensating the Doppler shift. It is possible to today connecting our mobile phones directly to those satellites.
Thank you.
Any further questions? Please.
Maybe related with the same topic, you mentioned about the Doppler shift. If I'm not wrong, the LEO orbits are moving 28,000 kilometers per hour?
28,000 kilometers.
Yes, how can we adjust Doppler shift? Maybe it's a basic question, but it's a very high speed for a mobile communication.
Yeah, I mean, there is a Doppler compensation algorithm already, like it's in the literature, where you can use, if you know where the
trajectory.
Yeah, if you know the trajectory, this is very deterministic trajectory, and speed is also deterministic, so it is easy to compensate, basically.
Thank you.
So if you know.
My question is related with that one. So you said that you mounted Starlink terminals on the car, Hocam, if I understand correctly. So as far as I understand, it can also support some sort of mobility, right? So, and also those antenna, I guess, should be mounted on top of the car,
Yes.
right? So dish antenna, as far as I know. So.
Yeah, exactly. That was a challenge to keep the antenna on top of the car,
Okay.
like, yeah.
Okay, so maybe we can end here. So, okay.
We would like to thank our dear presenter, the dear Associate Professor Dr. Çavdar. And we invite the Professor Dr. Ertuğrul Basar to present her gift. Now we are taking the 15-minute coffee break and convene at 4:30 for the fifth panel.